Alright, let's do another problem for today. Our next problem is going to be number 75, sort colors. Given an array nums with n objects colored red, white, or blue, sort them in place so that objects of the same color are adjacent, with the colors in the order red, white, and blue. We will use the integers 0, 1, and 2 to represent the color red, white, and blue respectively. You must solve this problem without using the library sort function. One pass algorithm using only constant extra space. So n time of one space follow up, though it's not necessary if we do it the first time around. Seems like a pretty decent candidate. Admittedly, I was doing some review on sort of the LeetCode patterns, and it was like this morning, and 2 pointers, and the problem, or some of the blogs I read were just basically, yeah, sort colors is a 2 pointers problem. But I think the rationale behind it makes sense. That we have a pointer to where basically the next object of a color would be, and we basically sort it into that partition after scanning through it. I think it makes sense to a certain extent. I just need to sort of map out like how that would look like. So let's see. Well, our first question is it guaranteed that a value will, or that a 0, 1, and 2 will exist in the array? I don't think this will change much, but 0, 1, and 2, if they exist within the array, that means that we know at least the array size is 3, though I guess given that the array size is at minimum 1, that means that that's not the case. But that does say that does give us an edge case that if the size of the array is 1, we can just return, because it doesn't matter at that point what color that ball is, or that color, what color that item is, because there's no other element to compare it against. Now, there's also no guarantee that we have an element. There's no guarantee that the elements are balanced in terms of their amount. So we really need to find like we could probably use multiple pointers for this one. Partitioning the array into sections. This is a 2-pointer problem, but I think we've seen 2-pointer problems use multiple pointers. How would this look? Well, let's think about it let's break this down into a simpler case. Let's think about a case of 2 colors first. Well, and we'll say it's like 0 and 1. Well, we want all the zeros in one spot, left adjusted. We want all of the ones in one spot, right adjusted. So in this case, we can say that if start a pointer at the left and the right, for the pointer on the left, move until we encounter a 1. For the pointer on the right, move until we encounter a 0. Swap. And then continue until the 2 are overlapping or crossing. Right. So basically we start at each end, if there's we move the left pointer, or I guess the right pointer because mirrored video, mirrored camera. We move this over until we encounter a 1. We move this right pointer until we encounter 0. And then we swap them so that they are in the correct area, and then we move along. Well, how do we handle the third color then? That's a good question. If a third color is thrown in, we don't really have a partition for them, right? We don't have just like the left and the right pointer. That's not quite what we have. Let me think. We could create a secondary partition for them, so we create a second set of 2 pointers. With the following rules. We will always hold a reference to the left edge of the middle partition and a right edge of the middle partition. On the left side, if we encounter the middle color, if we haven't encountered any so far, move the middle partition to that space. And do nothing otherwise. Similarly, on the right side, we move until we see a third color and plant the partition there. However, we need to make another change, and that is if we encounter the proper side color now, we want to shift it to the side edge. This means that what we will do is that we will swap instead of swapping with instead of doing nothing, we will swap with the third or middle color partition edge. So if we encounter, like, let's say blue, right? We have the blue on the right side. If we encounter a white color index, we'll leave it there, but we'll plant the partition there. If we then encounter some blue, what we will do is that we will swap the blue with the white, and then we'll leave the white partition, or we'll update the white partition and update the edge index. Similarly, on the left, we do the same thing, but just with red and white. The rules for the opposite color, though, still apply. I think that this is a decent approach. And this will take O of n time and no additional space. So let's actually get started coding. Nums.size minus 1. And we'll say that if our nums.size is 1, we'll just return, because there's no point in doing all this work for nothing. We'll say left, middle partition left is 0, middle partition right is num size minus 1. And while left is less than right, we'll do the following. Well, first left minus minus, or sorry, left plus plus, right minus minus, right? So we actually escape out of the loop. Then we can say that when num's at I, or when num's at left, actually we could do while num's left is equal to 0, left plus plus, while nums dot right is equal to 2, right minus minus. Right, so now we're at the case where the left and right have either encountered the opposite color or the middle color. And we'll say when num's left, if it's 1 and if it's 2. Or actually, we can just split it. Let's see. Actually, this is fine. When num's left is 1. If our middle partition left at nums is equal to 1, then we want to swap. So val temp is equal to nums. Actually, we know the colors, it doesn't really matter. So nums at left is equal to 1. Nums at middle partition left is equal to 0. And middle partition left is equal to left in that case. So we go here, we encounter a 2. Let's see. If nums at right is equal to 0, we can say nums at left is equal to 0, nums at right is equal to 2, left plus plus, right minus minus. Or actually, we can just keep on going like that. And then if nums.right is equal to 1, because we've already handled the case where it's, so we know that under here, we are for sure, both of them have encountered a color which is not according to what they need. We have already handled the case where both of them are of the opposite color, and we just swap them. And now we want to handle the case where the number on the right is the middle color. So if nums at middle partition right is 1, then nums at right is 1, don't need semicolon, nums at middle partition right is equal to 0, or 2 rather, and then middle partition right is equal to right, and then we just continue from there. So idea is like this, so 0 and 2, we swap them. So let's actually go through this in the comment space here. So 2, 0, 2, 1, 1, 0. The first one will be swap. Swap left and right. So now we go to here, and then we go to here. This encounter here with the right side. So we started here and here, that's where we stopped. And then we moved above here, and then we stopped at here. At this 1, well, what happens? Well, we check the middle partition right. The middle partition right is actually a actually, we could just do that. No, we don't want to do that. Well, we've encountered a 1. And we haven't, our middle partition right is still on the 2. And the 2 is not going anywhere. So we want to set the middle partition right. If middle partition right is greater than our right side, and similarly here, if middle partition left is less than left. So since our middle partition right currently is greater than our right hand side, so it's lagging behind. No, but it should lag behind, right? It should stay there. If we encounter another 1 here, we don't want it to move up. I wonder instead of that, if we should actually do it from the other perspective and say like the limits of where our yeah, I think that's actually what we actually want instead. So middle partition left plus plus middle partition right minus minus. So now our middle partition right is here, and that doesn't really do anything. No, but then this leaves that there. If we encounter a 2, or if we encounter an edge 1, we want to say that if nums at middle partition right is equal to 1, then we swap it with 1 equals 2. Is equal to here, I think. Oh, this is quickly unraveling into a bit of a more complicated problem than I imagined. In theory, it's pretty simple. Let's see. Give me some time to think. Let's see. So let's put it here. So last blue element would be the one after. Same with you. Let's think about you first. Encounter 1. I want to swap it basically. Want to swap it basically if we have 2. So if we do it like this, it does make sense that Maybe these belong at the bottom then. So these will move to where they need to, like here, and swap. And they'll move again. What do we want? We want to keep an eye out on the last blue element and last red element. Actually, I think it does make sense to keep it there then. So we don't go through with that, we swap it, right? And now we're at 0 and 2. Oh, and left is blue. Well, do we need to do this? I'm not too sure. Might not be necessary. Let's see. We swap it. We move it to the next one. Last red element. Well, this one is 0, so last red element becomes started off at 0. Or started off as 2. So now we move it up. So now it's at 1. That's fine. Here, we didn't do anything, so it stayed here. Because it's initialized there. Okay. If we encounter an element of which is not our color, like this one, then we want to swap it Do we want to swap it? This example isn't particularly great. Nums right is 1. Then we can swap it. So we actually have a few cases. Actually, so in this case, we just move until both of these are not at their own color. So then what? So now it's either the same color or the opposite colors, or a case where it's a middle color. So nums left is equal to 2. Nums right is equal to 0. nums right is equal to 2. So we just perform the swap there, and then we can go on our way, right? We can go on our way if we have encountered the opposite color. If there is a middle color, I think we also swap it. Let me think about this some more off camera. This is going to take a while. Okay, let me see if I can actually explain this in a way that makes sense. So, I updated the loops, the while loops for both the left and the right side. If we encounter an element of our same color that we want, we need to also make sure that it is in the right place. For it to be considered in the right place, we want to basically check to see if either the middle partition on their side does not exist yet, which means that so far we've only encountered our same color, so we can continue to do so. Or, in the case that it is not, so basically we have a middle partition, and that middle partition is earlier than we have so far, then we should swap. Basically, if we have this value, we just swap it and move up the middle partition. And the reason why we move up the middle partition to the left side is because that will be essentially our new... I'm wondering now if we should move the middle partition just up one rather than updating it to the left. Because when we are swapping, the idea is that if we have another left partition, we should only keep it at the point where it's needed. I'm not sure if this solution will work. Let me think about it a little bit more. Okay, let's see if I can actually explain it now that I've tested it with a few test cases, not just the example test case, but also one that I came up on my own, just randomly generating the numbers. So the main idea is that each side, each end, is responsible for managing its own sort of separation between its own colors. So so the left side is responsible for sort of maintaining the boundary between it and the middle, and then the right side is also responsible for maintaining its boundary between itself and the middle. So we don't care that much about swapping the ones. And then this basic while loop here basically says that if we encounter a value that is over our middle boundary, then we swap it, and then we move our boundary up by 1. Because if we encounter a 1, we assume that that boundary is just there, that the boundary exists there, and this boundary will always be the left side, the leftmost boundary for the left side, and the rightmost boundary for the right side. So we don't want to update it, except in the case where we need to swap it with a value that is appropriate. Then at the end, so now we have two essentially partitions where we have the value that it's responsible for partitioned, and the middle part partitioned. Any other value, it would be on the opposite side. So now we have the left pointer and the right pointer pointing to opposite colors most of the time. We swap them, and then we go to the next iteration. We don't actually increment or decrement left and right pointers here, because once we swap them, those numbers might not be in the right place, right? After we swap them to be in the right half, they might not be correct relative to the middle partition. So we then go back and we check those two numbers, and if they need to be swapped again, then we do so. At the end, we also check to make sure that if we have a center number that needs to be swapped, then we swap it with one side or the other. It really doesn't matter too much here in this case. I think that's about it in terms of the edge cases, or at least the edge cases that I could think about, and sort of just the algorithm as a whole. So the idea is that we build up essentially two mini problems where we have the left and the right partition, right? And then we sort of, once we encounter an opposite, then we swap them across the halves. And that's sort of how I imagine it. So let's give it a shot for actually submitting, and then we'll see if there's another situation that we need to think about, or if we do pass it, our sort of space. Okay, looks like we had an out of bounds exception. Let's see. Okay. So left and right are there. Because the inner cases don't really care too much about that that situation. Which is why I had to add this if left is less than right clause here as well. Honestly, in that case, I might just do situation here, left is less than right, and I think this is probably necessary to be a part of this, and probably most other situations, because we are actually manipulating the right side. We are actually manipulating the right and left pointers, so it does make sense to actually have a control sort of group there. I'm just going to run through my test cases to make sure that I didn't introduce any regression. I don't think it will, because I don't think I've really encountered this. 0, 2, 1, 1, 0. We don't need to test the other ones. And then, so that works. And let's just make sure that it works for this edge case that we didn't quite account for with the index. Okay, cool. Let's throw in another submit, and let's see if we hit another edge case or if we passed. Okay, looks like we passed the edge cases, or we passed all of the test cases, rather. So yeah, this is the sort colors with the 2 pointers pattern. Very, very messy solution, but I hope you learned something, and I'll see you for the next problem.